This is the second of our lessons on time. In the last one, we looked at Kepler's laws and the definitions of a day and a year. Kepler's first law, the orbit of each planet is an ellipse, with the Sun at the foci. In the last one, we exaggerated the amount of EST in diagrams in order to make this point clear. But in fact, the difference in distance between perihelion and aphelion is only about 3% of the average Earth-Sun distance over the year. The orbit is almost circular, so the difference in distance at summer and winter has very little effect on the climate. In the northern hemisphere, early January can be one of the coldest times of the year, but this is at perihelion, the time the Earth is closest to the Sun. So, as we suggested in the last lesson, the changes in the seasons must be caused by something else. The actual reason is the tilt of the Earth. All the 8 major planets orbit in concentric ellipses very close to the same plane. For the Earth, this is called the plane of the ecliptic. However, the axes they spin are different. For instance, Mars is at 25 degrees off, Uranus is 98 degrees off, and Venus is nearly 180 degrees off. Earth is 23.5 degrees the perpendicular of its ecliptic. This is what causes the annual changes in the seasons and the hours of daylight over the year. If we imagine between the centre of the Earth and the equator being extended out into space, we get another plane. This plane is called the equinoctial, and it is perpendicular to the Earth's spin axis. The angle between the ecliptic and the equinoctial is also 23.5 degrees. This is sometimes called the obliquity of the ecliptic. If this angle is 23.5 degrees, then the angle between the Earth's spin axis and the ecliptic must be 66.5 degrees. It is odd that the Earth's actual tilt in space changes over the year. For instance, this is the situation on the 21st of June. The Earth's axis inclined at 23.5 degrees to the ecliptic. This points to some fixed point in space, very close to Polaris, which can be taken as being fixed in space over a period as short as a year. 6 months later, the orientation of the Earth in space has not changed. It is still pointing. If we look at it from an Earth-centered point of view, this is the apparent path of the Sun's overhead during the year. In order to define points in space, we need a celestial reference system similar to latitude and longitude. With latitude, we take the equator as the reference and measure the elevation angle to some point on the Earth's surface. For celestial measurement, we imagine the equator expanded out into space to form the equinoctial, and again measure the elevation angle to some point in space. This angle, which is the celestial equivalent of latitude, is called declination. Declination is the angle measured northwards or southwards from the equinoctial to a line joining the centre of the Earth to a body in space. It is the annual change of declination which causes the seasonal temperature changes. Let's consider the Earth on June the 21st. The Sun's diameter is more than 100 times greater than the Earth's. Therefore, relative to the Earth, the Sun's rays arrive on a broad front. Imagine a square cross-section of this heat and light, with sides of, say, 1,000 nautical miles. And another one down here. Each of these cross-sectional areas in space contains the same amount of heat. However, the angle at which the heat meets the Earth at latitude 23 north means that the heat is concentrated over the smallest possible area. At 23.5 south, it is spread over a much larger area, and so the heat is less concentrated. The Earth is rotating about its axis, which is tilted with respect to the Sun's rays, so that the area of heating remains at the same latitude over a day. This situation represents a northern hemisphere summer or a southern hemisphere winter. 6 months later, the Earth is at the opposite end of its orbit, and so the Sun is directly over latitude 23.5 south. This gives us a southern hemisphere summer or a northern hemisphere winter. The latitude corresponding to the Sun's maximum northerly declination is 23.5 north. It is known as the Tropic of Cancer. Similarly, the latitude corresponding to the Sun's maximum southerly declination is 23.5 south. It is known as the Tropic of Capricorn. The regions of the Earth between these two latitudes are called the tropics, or the tropical zone, and they are the hottest parts of the Earth. The annual change of declination also causes the seasonal variation in the length of the hours of daylight. Again, consider the Earth on June the 21st. We'll take two positions on the Greenwich meridian, both experiencing local noon. One is at the equator, and the other at 40 north. The Earth now rotates for 6 hours, so that the local time for each of them is 6 p.m. You can see that the position at the equator is passing into darkness. However, the position at 40 north is still in daylight because of the inclination of the Earth. The Earth will have to rotate for another 1.5 hours before this point passes into darkness, when the local time is 7:30 in the evening. This is a northern hemisphere summer, when the daylight hours are longer. However, for the southern hemisphere it is winter. Their daylight hours are shorter. Here, the Earth has to rotate until only just after 4:30 in the evening for it to pass into darkness. 6 months later, the situation is reversed. You can see that the hours of daylight are now longer in the southern hemisphere. For them it is summer, whilst the northern hemisphere has its winter. One of the consequences of these changes in declination is the phenomenon of midnight sun at high latitudes at certain times of the year. Consider the latitude of 66.5 degrees north on June the 21st. The meridian facing the Sun is experiencing local noon. Local midnight occurs at its anti-meridian. Everywhere north of this latitude is in sunlight for a whole day. Similarly, everywhere south of 66.5 degrees south is in darkness for a whole day. Higher latitudes give longer periods of continuous light or dark, but 66.5 degrees north and south are the lowest latitudes at which it is possible to get at least one day of continuous light or of continuous dark, depending on whether it is summer or winter. They are therefore called the Arctic Circle and the Antarctic Circle. This is a graph of the annual declination of the Sun. As you can see, it looks sinusoidal in form. It would be a perfect sine wave if the Earth's orbit were truly circular. In practice, because the Earth's orbital ellipse is so close to circular, the graph is very close to sinusoidal. The declination of the Sun can therefore be considered to follow a sine wave, with a peak amplitude of 23.5 degrees and a cycle of 1 tropical year. The Sun appears vertically above 23.5 degrees south on the 21st of December. This is known as the Northern Hemisphere winter solstice and the Southern Hemisphere summer solstice. It then crosses the equator from south to north on about the 21st of March. This is known as the Northern Hemisphere spring equinox and the Southern Hemisphere autumn equinox. On the 21st of June, it will appear above 23.5 degrees north at the Northern Hemisphere summer solstice and the Southern Hemisphere winter solstice. And on the 21st of September, it crosses the equator from north to south at the Northern Hemisphere autumn equinox and the Southern Hemisphere spring equinox. These dates are not always exactly on the 21st of the month. This is partly because the precise date depends on the relationship between the year considered and the leap year cycle, partly because our calendar does not have the same number of days in each month, and partly because the orbit is elliptical, not circular, and the Earth travels at a different rate at different times of the year. However, the difference is never more than a day or two. The length of the hours of daylight at any particular latitude varies with the declination of the Sun. The rate of change of the length of daylight will therefore be greatest when the rate of change of declination is greatest. You can see that between about the 7th of March and the 7th of April, the declination changes by 20 degrees. A similar situation occurs around September the 21st. Therefore, the rate change of the length of daylight will be greatest at the spring and autumn equinoxes. At the summer and winter solstices, not only is it the flattest part of the curve, but it is also changing direction. There is hardly any change in declination, and therefore very little change in the length of the hours of daylight. This explains the origin of the words solstice and equinox. Solstice comes from two Latin words, sol and sticere, which means sun and to stand still. To the ancients, it seemed that the sun was standing still at midsummer and midwinter, because at those times of the year the days did not appear to change length. The word equinox comes from two Latin words meaning equal night, because at the spring and autumn equinoxes we get closest to 12 hours of daylight and 12 hours of darkness. Just as declination is the celestial equivalent of latitude, we also need a celestial equivalent of longitude in order to define the position of a body in two dimensions. This is called hour angle, and it is defined as the arc of the equinoctial between a datum meridian and the meridian of a celestial body. It is similar to longitude, except that it is always measured westwards. Let's look down on the Earth from above the North Pole. We choose a datum meridian. As the Sun or star transits the datum meridian, the hour angle is 0. In this example, another celestial body is 80 degrees west of the datum, so its hour angle is 080. Here we see the Greenwich meridian being used as the datum. Position 3 has a Greenwich hour angle of 050, which corresponds to longitude 50 west. Position 4 has a Greenwich hour angle of 180, which corresponds to the Greenwich anti-meridian. And position 5 has a Greenwich hour angle of 270, which corresponds to longitude 90 east. Note that it is not necessary to say 270 west. It is always west. If the hour angle is measured from the observer's meridian, it is called the local hour angle and abbreviated to LHA. If measured from the Greenwich meridian, it is called the Greenwich hour angle and abbreviated to GHA. Because the Earth is rotating, the hour angle is constantly changing and is only valid at a specific time. By contrast, declinations of stars are constant for many years. Even the Sun's declination can be regarded as constant over a period of a day. Let's summarize this lesson. The Earth's orbit is almost circular, so the difference in distance at summer and winter has very little effect on the climate. The plane of the orbit of the Earth round the Sun is called the ecliptic. However, the Earth's spin axis is at an angle of 66.5 degrees from its ecliptic. The plane of the Earth's equator extended out into space is called the equinoctial. The angle between the equinoctial and the ecliptic is therefore 23.5 degrees. The Earth's orientation in space does not change significantly and can be taken as constant over a period as short as 1 year. What does change, however, is its orientation relative to the Sun. Declination is the celestial equivalent of latitude. Seen from an Earth-centered point of view, the Sun's declination appears to change like this over the year. This annual change of the Sun's declination explains the seasonal variations in temperature. It also defines the Tropic of Cancer at 23.5 degrees north and the Tropic of Capricorn at 23.5 degrees south. They are the highest latitudes that the Sun can ever be directly overhead. The annual change of declination also explains the variation in the hours of daylight at different latitudes throughout the year. This gives us the definition of the Arctic and Antarctic circles at 66.5 degrees north and south. They are the lowest latitudes at which it is possible to have at least one day a year of continuous daylight or continuous darkness. The graph of declination is very close to a sine wave. It gives the most rapid changes in the length of the hours of daylight at the spring and autumn equinoxes in March and September. The longest and shortest days occur at the summer and winter solstices. Just as declination is the celestial equivalent of latitude, our angle is the celestial equivalent of longitude, in order to define the position of a body in 2 dimensions. It is always measured westwards. If the hour angle is measured from the observer's meridian, it is called the local hour angle, and abbreviated to LHA. If measured from the Greenwich meridian, it is called the Greenwich hour angle, and abbreviated to GHA. Declinations change relatively slowly, but hour angles change continuously as the Earth rotates, and must be referred to a specific time. This completes the second lesson on time. The next will look at the various forms of time used in order to cater for longitudes other than Greenwich.